One can clearly discern the precursors of modern scientific thought in the work of Archimedes. As both an engineer and one of history's paramount mathematicians, he stands alone as the only figure from Greek antiquity to make a significant, direct, and enduring impact on mechanics. His specific dedication to science, in the modern sense, was evident in his experiments, his emphasis on physically verifying theory, and his realization that basic principles described by mathematics mirror physical phenomena. Similar to Euclid and Lucretius, Archimedes exerted a positive influence on giants like Galileo Galilei and Isaac Newton. Plutarch characterized him nearly 2 millennia ago as a man possessing a superior spirit, a profound soul, and a wealth of scientific theories. We possess unusually detailed information regarding Archimedes' life, which is rare for ancient scholars. He was raised and lived the majority of his life in the Sicilian port city of Syracuse on the Ionian Sea. The walls, fortifications, and aqueducts of the ancient metropolis remain visible today. Born roughly in the year 287 BC, Archimedes was the son of Phidias, an astronomer, and was a friend and likely a relative of King Hero II, the tyrant of Sicily who ruled starting around 270 BC. At one point, Archimedes visited Egypt to study in Alexandria, the era's primary hub of Greek culture and science, home to the ancient world's vast library. In this city, Euclid had founded his academy a generation prior. Archimedes' legacy spans mathematical papers, practical inventions, and stories of his experiments. While some of his mechanics books have vanished, the treatises on geometry, the standard format for Greek mathematical discourse, survive in a sharp and energetic style. In On the Equilibrium of Planes, Archimedes proves the laws of levers and investigates centers of gravity. In On the Sphere and Cylinder, he discovers formulas for a sphere's volume and surface area. He came very close to inventing infinitesimal calculus, and his texts were standard reading for Newton and Leibniz in the 17th century. In The Sand Reckoner, one of his final works, Archimedes neared the invention of logarithms and utilized scientific notation for massive numbers. He estimated, for example, that 10 to the 63rd power grains of sand would fill the cosmos. The famous law of buoyancy, Archimedes' principle, is explored in On Floating Bodies. This principle states that when an object is submerged in fluid, it experiences an upward vertical force matching the weight of the displaced fluid. A pebble sinks because it weighs more than the tiny volume of water it moves. Conversely, a massive vessel stays afloat because of the immense weight of the water it displaces. Archimedes' principle clarifies why objects float and serves as a cornerstone of hydrostatics. Another application of Archimedes' principle stems from a legendary, though likely apocryphal, tale. King Hero suspected a wreath intended for him, not a crown as often claimed, was not pure gold, but contained some silver. Archimedes needed to find the truth without damaging the wreath, which would be sacrilege. Pondering this while bathing, the Roman architect Marcus Vitruvius wrote 2 centuries later, while he was sitting in the tub, he noticed water spilling over, equal to his submerged volume. Realizing this offered a solution, he leaped out and ran home naked, screaming at the top of his lungs that he had found it. Eureka! Eureka! Archimedes had discovered a way to gauge the density of irregular shapes. To check the king's wreath, he dunked it and tracked the displaced liquid. He then noted that an equal mass of pure gold moved less water. Thus, it was clear the wreath was a fraud. Archimedes is also credited with various practical innovations. The most renowned is undoubtedly the Archimedes screw, a spiral tube traditionally used to lift water. He also built a device mechanically modeling celestial motions, a type of planetarium. It appears Archimedes also devised the dioptra, an instrument to measure the sun's apparent diameter. Plutarch depicts Archimedes anecdotally as being so focused on math that he was absent-minded and indifferent to his appearance. He would trace geometric shapes in hearth ashes or on the oil he anointed his body with, forever consumed by a divine obsession and the joy science provided. Archimedes also had a sense of humor. He reportedly sent fake theorems to friends in Alexandria to prove that those claiming discoveries without offering proof are essentially discoverers of the impossible. Romans killed Archimedes in 212 BC during the invasion of Syracuse. Works by historians Polybius, Livy, and Plutarch indicate he played a vital role in the city's defense. They describe ballistic machines hurling boulders at Roman vessels and cranes dropping rocks onto ships. One story mentions an iron claw lifting ships from the water. While the tale of giant mirrors burning the fleet is undoubtedly false, it is no surprise the Romans only won after a protracted siege. Plutarch quotes General Marcellus asking his engineers, "How can we stop this man, who uses our ships as ladles and outdoes the mythical 100-armed giants?" Though Marcellus wanted him taken alive, the soldier sent to confront his intellect ended up killing him. Marcellus was distressed. A story philosopher, Alfred North Whitehead, later used to argue, with some exaggeration, regarding Roman deficiencies in the contemplative realm. Archimedes' favorite proof involved the relationship between cones, cylinders, and spheres. He showed that if these shapes share a base and height, imagine a cone inside a hemisphere, inside a cylinder, their volume ratio is 1 to 2 to 3. Furthermore, a sphere's surface area is 2/3 that of its enclosing cylinder. This relationship delighted Archimedes so much, he requested the figures be carved on his grave. A century later, Cicero, the famous statesman managing Sicily, hunted for the tomb, and I found it covered with bushes and brambles, he wrote. I noticed a small column rising above the brush, featuring a sphere and cylinder. While not the first to use levers, Archimedes seemingly solved the compound pulley issue, declaring the famous proverb, "Give me a place to stand, and I will move the earth." Thus he leads the list of scientists who followed, all of whom remain indebted to him to some degree.